Now we are going to discuss about the failure of classical physics. Now, last time we discussed about the intensity distribution curve for black bodies. So there, all of these curves are plotted using the practical data. That means you take a black body and change the temperature of it, and for different wavelengths, you are measuring the intensity of each wavelength and plot this graph. So all these data, all these curves has been plotted using the practical data. Then scientists tried to develop an equation to match with the curves or the practical data which has been used to plot these curves. But they all failed because they all tried to develop the equation based on the classical physics theories. In the classical view, so far we explain the things using classical, all those Newton's laws, and we also call them as Newtonian physics. All of those views are based on classical physics. So in the classical physics, we consider a wave is a continuous propagation of energy. Wave is a continuous propagation of energy. And also we consider when radiation is incident on object near the surface, it will absorb the radiation and become excited. So all the objects got particles. We call them as atoms. So when wave is incident on it, these particles absorb energy and they will go to an excited state, which means the high energy state. The excited particles will emit radiation to lose the gain energy and regain stability. That is, now you know, like they are in electrons, these atoms also have energy levels. So this is the lowest energy level. By absorbing energy, these particles can enter a higher energy level. So these atoms can enter a higher energy level depending on the amount of energy that they have absorbed. So this is the basics about waves according to the classical physics. So using the above classical wave physics attempt to explain the blackbody radiation. According to the classical physics, the wall of a blackbody radiator contains number of simple harmonic oscillators that emit radiation over a continuous range of wavelength. These oscillators are supposed to emit energy in any amount up to some maximum value. So all these particles or the atoms, they are in an oscillator. So you know, in any object, these atoms are always vibrating. They have vibrational kinetic energy. When they absorb energy, their vibrational kinetic energy also increases and they start vibrating with larger amplitudes. So to come back to the normal state, low energy level, these absorbed energy should be released. Then they can go to the lower energy states. So this released energy can have any energy value. According to the classical physics, it says this released energy can have any value. So based on those views, there are some scientists who tried to explain the blackbody radiation, the intensity distribution curve. One of them are these scientists, Rayleigh and Jean. So they developed a formula like this. based on the classical wave theory, but you can see this is how their graph came according to the equation. This is the practical graph. Practically what we obtained. This is the intensity distribution curve. And this one is the curve obtained using this equation. So you can see for longer wavelengths, it's the equation agreed with the practical data, but for shorter wavelengths, it didn't match. So there was a failure. Another scientist is Wiens. So Wiens also formulated an equation like this. You don't need to remember these ones. This is just to know that there are some equations that they have developed. But what happened here, this is what he got. This broken line shows that. And you can see there, for the shorter wavelengths, that equation matches up to a greater extent. But for larger wavelengths, there are some deviations. It didn't match with the practical data. So that Wien's equation is also having troubles because that one is also based on classical wave. There's another scientist who tried to develop another equation, that is Max Planck. He used a complete new theory to explain the intensity distribution curve that is known as the quantum theory. So Max Planck is the inventor of quantum theory, and it's a completely new theory, and there are some new views to explain the oscillations of the atoms and how the energy is absorbed and how they are released. So he has mentioned about the oscillations in the cavity wall, such as oscillations of atoms in the wall of cavity can take only certain discrete energy values and wavelengths. So this discrete energy values and wavelength is the main difference from the classical wave, because he has mentioned the atoms of a blackbody wall. They are vibrating and they have energy, but these atoms got discrete energy values, but not a continuous energy values. The lowest energy level of that atom is this, and by absorbing energy, they can move up to higher energy levels. So there are some discrete energy levels that these atoms can move. So in his hypothesis, he mentioned that a system which is performing simple harmonic motion of frequency f can only have values of energy which satisfy the equation E equals nhf. So this is the Planck's equation. And based on that equation, he developed another equation to explain the intensity distribution curve, and this equation completely matches with the practical curve. So in this diagram, you can see what he has mentioned. As I mentioned earlier, the atoms of the cavity wall, they have discrete energy values starting from 0 energy, 1, 2, 3, 4. But they don't have in-between energy values like this 1.5. Such in-between values are not there. 0.5. In between values are not there. And no such 1.5 thing. Or 2.4, no such things. Only after 0, then the next energy level is 1. After 1, the next energy level is 2. But in between values are not there. None of the in between values are exist there. So this n is the, we call it as the quantum number. So n consists only integer number like 0, 1, 2, 3. If n is 1, that is the lowest energy level. That is the lowest energy level. So for the smallest energy level, we can write the equation as E equals hf because n is 1. And when these atoms go to the higher energy levels, they need to absorb energy as radiation. So for example, if you take a certain atom at this point, if it wants to go to the next energy level, a certain energy should be absorbed as radiation. So this radiation will come and this atom will absorb this, the amount that this radiation, energy amount that this radiation has is equals hf, because from 0 to 1 the energy difference is hf as n is 1. If this atom wants to go to the next energy level, passing the first one, if it wants to go to the second energy level, then it has to absorb more energy than here. So the amount of radiation energy absorbed by the atom should be equals to hf. Because it has to go from 0 to second energy level. So the energy difference here is 2hf. So that much of energy should be absorbed. Like that, all these radiation got discrete energy values, like the smallest energy one is hf, the next energy level is 2hf, the next energy level is 3hf, like that it goes on. But no such 1.5 hf, those in between values, fractions, decimals are not there. Only integer numbers are there. So that's the Planck's hypothesis. But in the classical wave, we didn't consider the wave is moving in discrete amounts. We just mentioned the wave is moving in continuous way. And any energy value can be there. So this is the classical wave, and nowadays it's not the actual status. This is the one that we are going to describe. So these discrete energy values as hf or either 2hf or either 3hf. These discrete energy values, we call them as energy packets because this is one amount. This is another amount. And this is another packet amount. So these packets are known as quanta, singular quantum. So as I mentioned earlier, if n is 1, you get the lowest energy packet. The energy of the lowest energy packet is given as E equals hf, as n is 1. So this f is the frequency of the wave. So frequency can be written as also c over lambda. There C is the speed of light. The speed of light divided by wavelength, you get the frequency. And this h is known as the Planck's constant. H is Planck's constant and the value is also given here. So this is the Planck's quantum theory. Then there's a comparison between Planck's quantum theory and classical theory of energy. In the classical theory, we consider energy of an electromagnetic radiation is continuous. So continuously they flow. But in Planck's quantum theory, we can consider this radiation energy is quantized. Quantized means separated, discrete. So the wave or radiation doesn't move continuously, but they move as separate packets. And the second one, energy of an EM radiation does not depend on frequency or wavelength. So in the waves, if you can remember, in waves, we mentioned energy is proportional to amplitude, A squared. But now under the quantum theory, we know the energy depends on frequency. In classical theory, it's the amplitude. Quantum theory, energy depends on frequency. So that is the end of the first part of the lesson. The next part will be photoelectric effect. Thank you for joining.